How do transmission line models work in power systems? Imagine trying to send a message across a long wire. The way the message travels depends on the wire's properties. That's what transmission line models help us understand in power systems. They are like detailed maps that show how electricity moves along power lines. These models are essential for making sure electricity reaches homes and businesses safely and efficiently. Power lines are made up of tiny sections, each with specific electrical traits. These traits are resistance, inductance, capacitance, and conductance. Resistance is how much the wire opposes current flow, turning some energy into heat. Inductance is related to the magnetic field around the wire, which affects how quickly current can change. Capacitance is the ability of the wire to store electrical energy between conductors. Conductance measures how much current leaks through the insulation between wires. Engineers think of the entire line as a series of tiny segments, each with its own resistance, inductance, capacitance, and conductance. This way, they can analyze how voltage and current change along the line. There are two main ways to do this. The first is called the distributed parameter model, which treats the line as a continuous system. It uses differential equations, called the Telegrapher's equations, to describe how electrical signals behave at every point along the line. This model is especially useful for very long lines or high-frequency signals where wave effects like reflections matter. The second approach is the lumped parameter model. This simplifies the line by combining all the distributed properties into a few discrete components. It works well for shorter lines or lower frequencies where wave effects are less important. This makes calculations easier and faster. A key idea in transmission line models is the characteristic impedance. This is a special value that depends on the line's parameters. It tells us what the impedance of the line would be if it were infinitely long. Matching the load impedance to this value helps prevent power from bouncing back, which can cause losses and instability. In real power systems, engineers use these models to predict how voltage and current change as electricity flows from generators to consumers. They help determine how much power can be transferred safely, how to avoid faults, and how to design protection devices. They also help in understanding how the system responds during different conditions, like sudden changes in load or faults. In summary, transmission line models work by representing the physical electrical properties of power lines through these parameters. They allow engineers to analyze and improve the flow of electricity across vast distances, ensuring reliable and efficient power delivery in our daily lives.